doesn't it look like it follows the pattern of A union A intersect B, right guys? So what does that turn into if I go ahead and use the absorption law of that? A intersect B, right guys? So this is just going to turn into A intersect B complement equals A minus B. Okay. So does everybody see that, guys? The absorption law, that's going to take care of that. Okay. You have to think of the parentheses as singular A. Okay. So that's just its own set. Okay. And that's going to be by, what did we say? Absorption? Absorption. Okay. Yeah. Then we're done, right? Yeah, we're literally done because what do we just have a set difference here? Yeah, A minus B equals A minus B. So that's our set difference. Okay. So, unfortunately, this was one of those types of problems where we had to utilize the distributive property on a quantity. Okay, we don't like doing that, but unfortunately in this instance we have to. Okay, and I think number 9 on your homework, you might have to do that as well. Try to model number 9 after what we did here to try to assist you with that. Okay? All right. So, any questions?
So this is a pretty good test question.
You know, I wouldn't put something maybe of this high caliber question on the test because what I try to do is on the exams, I try to give you guys like middle level problems. I don't try
But
to.
it would utilize a double complement though, right? Most likely. Is that what you're saying?
Oh, I mean, double complement. I mean, that's a really, really easy one. But I wouldn't say, like, I wouldn't make it so that on the exam you guys can have to distribute a quantity. Okay?
Oh.
So, but, I mean, double complement.
That's what
sure.
I meant, that's what I meant.
Oh, I see, yeah. Okay. Yeah, I mean, I think that might be more difficult than necessary to test intermediate level knowledge. Okay. All right, other questions I can answer for you guys about anything before we move on?
It's not a question, but only 2011.
Oh, was it? Okay. So, wow. Jeez. That was what, like 6 years ago?
But I've taken other courses in between of them.
That's how you got so smart. Okay. All right. Other questions, guys, I can answer before we go ahead? Okay. So the next thing we're going to take a look at is we're going to take a look at counting methods. Okay. So hopefully this is going to be a little bit of a reprieve from what we've done because there's no proofs in what we're doing with counting methods. Okay. Most students do very, very well with the counting method stuff. So let's go ahead and knock some of that out. Now, unfortunately, due to our power losses, I have to reboot the computer and bring back up the things so I can see what I'm doing here. So bear with me for one moment.
If you have an extra copy, you can just use the paper.
Yeah, but I like being able to like demonstrate using the boards. That way everybody knows where I am exactly. So sorry, I'm one of those teachers that likes to use pedagogical implements and stuff like that. So plus my obsessive compulsive disorder doesn't like it either. So we'll go with that. It's more selfish than anything.
Oh, we did this in statistics, this kind of stuff.
Yeah, some of it is statistical.
Yeah.
Okay, I mean it's not high-level statistics. It's not inferential. It's all descriptive.
Yeah.
But I mean, some of the same things you guys might have seen in some of your stat classes.
Informational the alpha level, right? 0.05, 0.03.
Yeah, that's more of an inference.
Oh, those are interesting, very interesting.
Yeah, when you use a hypothesis test, all that fun stuff. Oh, you said statistics, and I clicked on my statistics class. It's the,
Ho and high, right?
my bad. Okay, I'm going. Da, 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 da. Counting methods, yay. Your download will begin shortly. Shortly as in like, yeah. I mean, 10 minutes compared to the length of time the world's been in existence is a short amount of time, so. I guess they're not lying. Oh, go away.
You killed it.
I killed it. It's killing me. There we go. Okay. So, when we talk about counting methods, I think one of the most fundamental things we can do is we can create something called a decision tree. Because basically, born of every sort of outcome is a decision tree. Okay? We could do this for any problem that we're going to look at in this class. However, they're very painful, which is what we're going to see. Okay? So, let's say for some reason I have a scenario where I have a red, blue, and a green marble that's placed in a bag, and I choose 3 of them at random with replacement. Okay? So, and I just go ahead and reach in there and grab it. So let's say for a decision tree, I have draw number 1. Okay, I'll just label this as D sub 1. The 3 possible outcomes that could occur, so this is our decision tree, would be that I could draw a red marble, I could draw a blue marble, or I could draw a green marble. Now, contingent upon what happens on draw 1, that's what's going to happen, then a different event might happen on draw 2. So, let's say for some reason I picked a red marble on the first draw. Then I put the marble back in the bag, and what are the possible outcomes that could happen on the second draw?
Same thing.
Same exact thing, right guys? So, for the second draw, we could draw either red, blue, or green. Okay? Same thing if I picked a blue marble, right guys? So this could be red, blue, or green. Same thing if I have to draw the green marble. Okay, so red, blue. All right. So this could be potentially draw 2. So I'll label this D sub 2. Okay. And any one of those could occur because it's a completely random event. Okay? And when we say random, it means that humans can't influence the outcome of that. Okay? Most of the time when we study probability and statistics, we talk about random events. Okay? We're not necessarily worried about conditional events. Okay? It's just because those are unpredictable for us to be able to try to formulate anything for. Okay? On draw number 3, what could happen if I drew 2 red marbles? Same thing, right guys? So I could draw red, blue, green. And then guess what we did to do a whole bunch more times? The exact same thing.
Can we just do like a double quotations?
No, sir. Unfortunately, efficiency won't work in this instance. Red, blue, green. Yeah, and then unfortunately, this is what your decision tree is. Okay, so green. Good thing I didn't make it 5 draws, right? Then you guys would just get that one wrong because you just didn't feel like doing it. Although not saying you feel like doing this one. Only 2 more. And then finally, all right. So that's our decision tree. Okay, so I'll give you guys a minute because I know you know how to do it. It's just getting there, sitting there and doing it. But basically what you guys would do is you would just trace it to list out all the possible outcomes. Okay? So for instance, one possible outcome from the decision tree is that I draw 1 red, 2 red, 3 reds. So one outcome would be red, red, red. One outcome would be red, red, blue. One outcome would be red, red, green. Okay.
Oh, you're doing permutations?
What's that?
Permutations?
There are permutations, right? Because the order, well, they're actually, believe it or not, they're actually more combinations because the order really doesn't matter. Okay? Because you can't really decipher one red marble from the next red marble. It doesn't really matter. Unless for some reason you're worried about what order you get them in. Okay? All right. And then you guys can do the same thing, okay, all the way down. Okay. But guys, that's all a decision tree is, okay? And like we said, everything that we do in this class regarding counting methods could go back to a decision tree, okay? So if for some reason, like if you guys are in another class and you're ever confused about a problem, just go back to the decision tree, okay? It's the easiest way to do it, okay? It might not be the most efficient way, but at least you guys could formulate an answer, okay? So does that make sense as to what a decision tree is, guys? For those of you guys that are computer science majors, trees are probably one of the most useful data structures that you guys could use, okay? So you guys could probably see where this would lend itself, especially to a binary operator such as a computer, to where you only have one of 2 things that could happen. You could either take the red or not take the red.
Can I ask you a question?
Yeah.
Why did you choose 3 trees? Because there were 3 marbles? Is that how?
Yeah, exactly. Just because, well, there were 3 possible outcomes.
Uh-huh.
And then it said to pick 3 different, and 3 of them are chosen at random. So basically you do 3 selections, okay?
Gotcha.
So if I said that there was only a red and blue, then there would only be 2 stems, but there would still be 3 levels, okay? So this would be like a parent and then some other child nodes, if you would. Okay, does that make sense, Oren?
Mm-hmm.
Okay. Other questions, guys? Okay. So let me show you guys an example as to why this thing would ever be useful, okay? So another question I have here and this can relate itself to probability a little bit. 3 people have been exposed to an illness with a 50-50 chance of becoming ill, okay? First of all, we want to list all the outcomes if all 3 people are examined, okay? So, what are the possible outcomes that could occur from this, guys? Like if a person's looked at,
He's either is
either ill or well, right? Either sick or not sick, okay? So, let's say we run into the first person, okay? So we examine person 1, and person 1 is either, I'll just say ill or well, okay? Just to make it easier, right guys? I don't want to use 2 letters that look the same and I and W look pretty different. Then based upon the first person's illness or wellness, we could say, well, person 2 is going to be either ill or well. Ill or well. And then we can do the exact same thing one more time. Okay, so, now this is one, because the next questions deal with probability, this is one where I probably want to list out all the possible outcomes that could occur. The other one I didn't list them out because, you know, I don't want to sit there and list out 27 outcomes. But this one only has 8, okay, so it's not that big of a deal. So one possible outcome is if I examine all 3 people happen to be ill. So ill, ill, ill. Another possible outcome is that the first 2 people are ill, but this third person is well. And then I would have ill, well, ill. I-W-W, and then W-I-I. So see what I'm doing, guys? I'm just tracing the tree. And then W-I-W. And then W-W-I. I know, I just thought about that.
then
And then
www.
W-W-W. I also saw way up here, W-I-I.
World Wide Web.
And then World Wide Web. It's really neat how many different permutations and how many different words or acronyms that we can actually get out of W's and I's.
I didn't know we were one of it.
Yeah.
It's a history class.
Oh,
That's how
no,
you
no,
guess how we're all rolling.
no thanks. We stay away from history.
Yeah.
So, does that make sense, guys? Nice and easy, right? Okay. Now, the second part of the question says, what is the probability that only one person is ill? Okay, so we look through the list, okay, and what we want to do is we want to figure out how many outcomes only have one person that's ill. Well, I take a look at it, and I have one outcome here that's favorable, I have one outcome here that's favorable, and I have one outcome here that's favorable. So those are the number of ways that I could select getting one person that's ill. How many total possible outcomes are there? 8.
8.
So what would the probability be for that?
3, 8.
3 out of 8, right guys? So there's a 3 in 8 chance, okay, that if I line up 3 people and they have a 50-50 chance of it being exposed to a virus and contracting it, then that they would actually have one of those would have the virus, okay? 3 out of 8 is 0.375 or 37.5%, I believe. Okay, you guys can check that in your calculator. So it's not highly likely, but it's not highly unlikely either, right guys? So it is possible that at least one person, or I'm sorry, it's likely that one person could be exposed to the virus, okay? What's the probability that no people are ill, okay? So guys, what would that be?
That's 1 out of 8.
Yeah, that'd be 1 out of 8, wouldn't it guys? Because there's only one way that all three people would be well, or no people are ill. So this is where maybe 0 people would be ill. Okay, so that would be 1 out of 8, or that's 12.5%. Okay, so it's not very likely that if there's a 50-50 shot of 3 people trying to contract, or not trying to, but being exposed to a virus, that nobody's going to get exposed to it. Okay, it's highly unlikely. Okay, and then the last one we have: what's the probability that either 2 or 3 people would be ill?
4 out of 8.
That would be 4 out of 8, right, guys? So there's 3, 2, 2, 2. That's 4 out of 8. So there's a 50-50 shot that either 2 or 3 people.
Actually, if you add the 37.5 and 12.5, you don't need to do the other one.
Well, right, but and then we would have to take the complement of that
Yeah.
to be able to work it, okay, which we'll have to talk about a little bit later. Okay? Alright, so guys, do we see what decision trees are useful for? Okay, and again, it's not one of those things that's difficult, but again, it's fundamental, okay? It's basically the building block of probability, if you would, in counting methods, okay? So any questions about that, guys? We wish the whole exam was counting methods, right? Not proof by mathematical induction, which we're not gonna look at on the next exam. Okay, one of the most useful rules is the multiplication rule, okay? Multiplication rule says that if m is the number of outcomes for an event A, and then we also have that n is the number of outcomes for event B, then the total number of outcomes for A and B is m times n. In fact, we could have seen that earlier when we had the example with the marbles, right? Because we had 3 marbles, right? And we were selecting 3 of those. So we would have 3 times 3, which would give us 9 outcomes on the second draw, and then times 3 more, which would be 27 outcomes, okay? So I just wanted to show you guys that the multiplication rule is actually relatable to what we were already doing. Like for instance, okay, for the sick and well, there are 2 outcomes, right? It's either sick or well, or ill or well. 2 times 2 gives us 4, times 2 more gives us 8, right guys? So we can still use the multiplication principle to see the number of outcomes. Now what's the problem with the multiplication principle? It doesn't show us exactly what those outcomes look like, right guys? So there's drawbacks to it. It tells us how many, but it doesn't tell us what the outcomes
So
look
the outcome will have to be exponent then, and the,
It could be exponential if it's binary, okay?
Okay.
But it doesn't necessarily mean that all are going to be binary, okay? So I don't want you thinking that it's always exponential, okay? All right, other questions, guys? All right, let's take a look at some examples where the multiplication rule could be utilized. Okay? So, we have an alarm code. It can be chosen from any of the 26 letters of the English alphabet, okay? How many 3-character codes could be created if repetition is allowed, okay? So here's the way I think about these guys. I just make 3 spaces. You have an alarm code, so you put 3 spaces in. Okay? There's 26 letters in the alphabet, okay? So how many letters could we select for the first